Assalamualaikum, brothers and sisters. Yeah.
Waalaikumsalam.
Okay. Good, everybody in. Shall we start? Sister Faika? We should start, right?
Yeah.
Okay, we should start. Okay, let's start our day with the recitation of Ummul Kitab Al-Fatihah. A'udhu billahi minasyaitanir rajim. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Arrahmanir rahim. Maliki yaumiddin. Iyyaka na'budu wa iyyaka nasta'in. Ihdinas siratal mustaqim. Siratal ladzina an'amta 'alaihim ghairil maghdubi 'alaihim waladdallin. Amin. Okay, as usual, let's start our day with recitation of dua. This time led by Ustaz Al-Imran. Tafadhal Ustaz. Ustaz Al-Imran.
Yes, Doctor. Can you hear me?
Yeah, I can hear.
Amin. Bismillahirrahmanirrahim. Allahumma alhimna ilman na'rifu bihi awamirak wa na'rifu bihi nawahiyak warzuqna. Allahumma balaghata fahmin nabiyyin wa fasahata hifzil mursalin wa sur'ata ilhamil malaikatil muqarrabin wa akrimna. Allahumma binuril ilm wa sur'atil fahm wa akhrijna min dhulumatil wahm wa aftah lana abwaba rahmatik wa 'allimna israra hikmatika ya rabbal alamin. وصلى الله على سيدنا محمد وعلى آله وصحبه وسلم والحمد لله رب العالمين.
Amin ya rabbal alamin. Thank you, Ustaz. Okay.
Ya,
Okay, now we are ready for the day. Let's imagine you are having a cottage industry. Then you are trying to produce some vase, V-A-S-E, vase. Let's say you have two types of vase. One is something like this in the picture, and the other one is something like this. Let's name this one with short neck. The other one is long neck. Let's name it as Sean, the model. The other one, we model it as lawn, long neck, lawn. And then you are going to sell this at 120 ringgit for the model Sean. And then lawn, you are going to sell at higher price, 140 ringgit. And then it costs you to produce Sean or short neck vase, 80 ringgit. And then long neck or lawn, it will cost you 90 ringgit. What will be the profit for short neck? Selling price 120, your cost is 80. What's the profit per piece?
40.
40. How about the second one, the long neck? What's the profit? Selling 50. Okay, good. Now you have a budget about only 6,000 ringgit, let's say. And then to produce this one, you require 30 minutes to make, 30 minutes of labor. And then the long neck requires 40 minutes to make. So the first one, 30 minutes to make, and it requires 200 grams of clay. The second one requires 220 grams of clay, let's say. And then you have available in your workshop only 10 kilograms of clay. And then the other one, the labor hours, you are allocated about 30 man hours. You are allocated 30 man hours. Now the question is, how many units? What is the best number? How is the optimal number? How many units of Sean and the how many units of loan to produce in order to maximize profit. Anybody have any idea? Well, we can linear programming. Yes, linear programming. This is the thing. So we have to use linear programming. You have done linear programming before? If you have done, then easier for us.
Yes.
Yes. So
In
we have
the
in, I don't know, you do which method? Graphical.
operational research subject.
Operation research. Okay. Then easier for you, but I still have to cover for some student who is not doing operations course. I think some of our class member are from economic department, from business department. So to be fair to them, let's cover the class. Otherwise, I can just back up. Okay, let's move on. What is linear programming? So in most situations, companies or organizations are constrained by resources, man-hour resources, your budget, capital, then equipment, tool, and many others. You are limited with the resources. At the same time, we want to get the best out of these limited resources. We want to maximize gain. Right? In company, we always to get the best. We want to get the best profit or the highest profit if possible, as much as possible with the limited resources. So how to do this? We are going to use linear programming. Okay, let's do a little bit of background. The background of linear programming started by these mathematicians, Russian mathematicians. I do not know how to pronounce this. Kolmogorov and Kontorovich introduced the early concept of this linear programming. And then independently, this Danzig in 1947, the American Force mathematicians used linear programming to solve the Air Force planning problems within the resources they have. And he developed what he called simplex method. Then there are many different types of mathematical programming: linear programming, goal programming, stochastic programming, fuzzy. I think you will hear some fuzzy logic. You want to buy washing machine. I think this some of the sales people say, oh, they has fuzzy logic. I think they have the logic actually is using algorithm or fuzzy programming, integer programming, dynamic programming, non-linear programming, fractional programming, multi-objective programming. Of course, there are some others. I just name a few here. Linear programming is used in many different disciplines, many areas, in the military forces, in agriculture, in engineering, economics, business, and even in politics. There are many others. Even like you want to decide ingredients for certain fertilizer productions. It is in agriculture. Because of course, linear programming, the purpose or the objective is to maximize profit. If you are profit-oriented organizations, if you are in NGO, non-profit organizations, you want to maximize effectiveness. If you are looking into costs, you are trying to minimize costs. Then other applications, product mix. If we are just now, our example is product mix. Which model A, model B, portfolio investment. Say you want to invest in certain stock market. What are the best decision? Which portfolio you want to invest? Advertising mix. Just now I give example like in the pharmaceutical product, you want to decide the ingredients. Agriculture, you want to decide the ingredient. Even sometimes as simple as restaurant, you want to decide ingredients to give you the cheapest cost, and many more. Again, objective function in linear programming, some of the element is objective function. What's object function? Function is mathematical equations. So the mathematical equations that represent the purpose, the objective. So we call it objective function. So the problem, I mean, from verbal statement, we are translating into some equations. So problem formulated as linear programming model with a single objective function. There are also situations, multi-objective programming. The problem consists of more than one purpose, one objective functions. But for our purpose, we are focusing on a single objective function. Then in many situations, we have limitations like constraint, all the resources, just now we have limit. Like you are in business, you have limited capital, or limited manpower, limited equipment, limited whatever technicalities. So this is referred as constraints or resources. These are the limited restrictions that limit the degree of the objective being pursued. So we cannot have everything. We want to achieve our objective within the limited constraint. So this linear programming is a combination of equation of the objective function and also the equation for the constraint. And then this become a set of mathematical equations that we are going to solve. There are certain assumptions behind linear programming. Certainty. Values of parameters are known with certainty. Say, if a product we have, say, 40 ringgit profit or 100 ringgit profit, it is not probabilistic. That means 40 is 40. It's not, it can be 41, 42, or maybe 45. So we assume all the numbers are fixed, I mean certain. Proportionality, that means something can be multiplied, linear, and then something can be added, additivity, objective function and constraint can be added, can be multiplied. Divisibility can be divided. That means variable are continuous numbers. It's not discrete numbers. And then we are dealing with items, with goods. Just now, our vase, it is an item. So item cannot be negative. Item cannot be negative, so we have what we call non-negativity assumptions. Okay, model formulation. What is model in mathematics? So we have this decision variables, common components and characteristic of linear programming model, decision variables. For example, just now, vase A can represent as x1, vase 2, x2, or xy, whichever we choose. But typically, we use x1 or x2, x1 and x2 and x3 and many more. Then we have objective functions using the variables. We formulate using equations for the purpose. Then we try to develop the equations for the constraint. The constraint is made up of all the decision variables and the parameters. Say 10 hours for 10 hours to produce, say, item 1. So the parameter is 10. Decision variables will be the x1. Again, in linear programming, the objective is either maximization or minimization. Formulations, normally we pick up from the verbal statement or the numbers, numerical information, and then to make it easier, we put it in tabular form. After you have certain experience, you do not need any more tabular form. You look into the statement, you can formulate. So the method of doing linear programming, there are 3 steps. The first one, decide the decision variable. X1 represent the number of units for something. X2, the number of units of another thing. The next one, develop or construct the objective function, the equations. Then we also develop or construct the equations for the constraint. Okay, let's have fun. In here, as a supervisor of a production department, you have to decide the daily production totals of a certain product that has 2 models, deluxe and special. 2 models, deluxe and special. The profit for deluxe is $12 per unit or 12 ringgit. And then special, 10 units, $10 per unit. Then each model go through 2 phases of production process. The first one is the construction stage. The second one is the finishing stage. So each model goes through 2 phases in the production process, and there are only 100 man-hours available daily at the construction stage, and only 80 man-hours available at the finishing stage. Each deluxe models require 20 minutes of construction time and 10 minutes finishing work. Finishing may be painting or varnishing, packing, whatever. Let's group into finishing. Each special model requires 15 minutes to construct and then 15 minutes to do finishing work. And then the management of the company has also decided that the special model must be made up or must comprise at least 40% of the total production. The question is, how many units of deluxe model and how many units of special model the company should produce so that the profit is maximized? So we are looking at maximization problem. What's the first step just now? Develop this tabular form, summarize it. So we have after that formulation, let's look into this one first. We have pick up the information from here. Let's look back. Construction stage and finishing stage. Construction stage and finishing stage. We tabulate here construction and finishing. Then we have deluxe and special. We have profit here. Okay, let's look back. Where's the profit for deluxe? Can you remember? Okay, let's look back. Profit for deluxe is 12. For the special is 10. Special is 10. Okay, let's put it here, down here. Deluxe 12, special 10. Construction time. Okay, that's construction time. For construction time for deluxe, 20 minutes to construct. And then special, 15 minutes to construct. And then you have available 100 hours. Okay, let's put in our table. 20 minutes, 20 minutes, and you have available 100 hours. Since it's minutes, we make it equal. So all I put it in minutes, 6,000 minutes. The same goes on finishing time. Finishing time for, we have available 80 man hours. And then finishing time for deluxe, 10 minutes. For the special, 15 minutes. Take note, 10, 15, 80. 10, 15, 80. 10, 15, 80 hours. Let's convert this into minutes. We make it into 4,800 minutes. So we have summarized this. Let's do the, what we call it, linear programming model or formulations. Just rather say formulations. Brother Ashraf, was it? Not so sure. So we decide what is X1. Let's say X1 represent the number of units for deluxe. X2 represent the number of units for special. Okay. Now let's develop the objective function or equations. How to develop? Maximize or minimize?
Using
Maximize, right?
maximize the profit.
Maximize profit. Okay, maximize profit. Maximize, let's say Z is represent the profit. 12, 10. X1 represent the number of deluxe. X2 represent the number of special model. Where did we get this 12? We know the profit.
Yes.
Okay. We know the profit from here, 12 and 10. So each unit generate 12 is 10 units.
Sure.
Let's say from here, if I were to produce 1 unit of X1, means deluxe, and 1 unit of special, what's the profit like?
22.
22. If I do not do,
22.
yeah, good. If I do not do anything, I produce nothing. I do not produce deluxe. I do not produce special model. Where's the value of
Zero.
X? 0. X1 is 0. X2 is 0. Your profit is 0. 0. So that's, we have construct the objective function. Now, let's look at the resources or constraints, limited resources. What was it? Construction time. We have 20 minutes for each deluxe, 15 minutes for each special, and then the department make available for you 6,000 minutes. Okay, let's formulate it into mathematical equations. So this is the mathematical equations or the constraints. 20 x1 plus 15 x2. What does it say just now? You are given 6,000 hours. Can you spend more than 6,000 minutes? Can you use more than 6,000 minutes?
No.
No.
Oh,
No. If you do not,
No.
no. If you do nothing, what happened to this one? You produce nothing. So it is available, but you don't use it.
Not yet.
not use. So you can use anywhere from nothing to up to 6,000. Agree? Agree.
Yes.
Agree. So this is, we have to put a symbol, inequality here, symbol. So we can use less or equal. We can use up to 6,000, not more. What is the second one? What are the constraints?
Finishing time.
Finishing time. So each deluxe require 10 minutes. Each special require 15 minutes to do finishing work. And then you are given 4,800 minutes. Okay, let's put the equations. 10, 15. You can only use up to 4,800 minutes. And then we have another constraint. The office specified the company has decided that the special model must made up of at least 40% of total production. How are we going to do this? What does it say? The company
X2 more than
X2 more than
2 more than equal to 40 x1 plus x2. 0.4, sorry.
Okay, so rather say X2 more than, at least it says
At least more than or equal to
40% out of 100. Agreed?
yes.
And then total is X1 plus
plus
X,
x2.
X2. Yes. So now, how to simplify this? So let's simplify this. So 10 X2 more or equal to 4 X1 plus 4 X2. Agree? Because you have to agree. So now let's put all let's put all on the left hand side. Can I rewrite whichever directions? Negative 4x1. I bring this one to the left, and then 4 bring to the left. So I'm left with 6
Plus x2.
x2 greater or equal to 0.
Then or equal to 2.
Yeah, agree? Yes, agree. So we have the third constraint, this one, negative 4x1 plus 6x2 more than 0. So this is the requirement from the management. Special must be 40% to 40% of total productions. Since we are producing a product, we have we call it non-negativity constraint. So x1 must be greater than 0. X2 must also be greater than 0. So units cannot be negative because we are dealing with items. Okay, now let's have a go. So this is the model that you had developed. Actually, this one, the same one. Now, how to solve? Since the title of our course is linear programming, graphical method. So we are going to draw graph. Simple. So let's draw the graph, something like this. And then on the x-axis, represent x1. Then the vertical axis represent x2. These numbers 100, 200, 300, 400, 500, 600 are the number of units for x1. The same thing on the vertical axis 100, 200, 300, 400, and so on, or 500. This represent the number of units for x2. If I were to say, if I were to put at this point or the coordinate, what does it represent? X1 equal somewhere here. X1 equal what? If I were to put some point here, somewhere here, what's the value of X1?
Oh,
Roughly
200.
200. What's the value for X2?
200 also.
200. So any point here represent what we call it solution point. That means we can, if I were to have, if I were to choose a point here, X1 is 400, X2 is 200. If I were to choose a point here, let's say a point here, so we refer anything on the right hand side here is solution point. And then we cannot have anything on the left hand side because X1 is greater than 0. X2 also greater than 0. So nothing less than 0. Okay, let's plot the first constraint. How to plot this? Linear programming. Remember, we use linear programming. We are going to draw lines. Linear equations. This is linear equations. So we are going to draw a linear equation, a line. What we need is we need 2 points. 2 points, and then we take the maximum. Take the maximum as if it is equal to up to the limit. So how to do? Okay, let's try to find the coordinate. If x1 is 0, somewhere here, if x1 is 0, what is x2? If x1 is 0, can you get x2?
400.
400. 6,000 divided by 15, you get 400. So you put a point here, 400. If x2 is 0, if x2 is 0, f2 is somewhere here, we try to find x1.
300.
300. So we put a point here, then we draw a line. If I were to produce 300 x1 deluxe model S1 and 200 units of special model, that means I try to choose this coordinate. Do I comply with this constraint or not? Do I satisfy this constraint? No. I violate this constraint, right? That means I don't satisfy this constraint. If I were to produce 100 units of X1 and 200 units of X2, somewhere here, do I fulfill the, do I comply with the limitations I have?
Yes.
Yes. And then X1 also greater than 0, X2 greater than 0. Now let's find what we call it the feasible area of the constraint. So this is the feasible area. That means if we construct 100 unit of X1 deluxe, 100 unit of X2 special model, we are satisfying this constraint. 20, the first constraint, that means the construction hours. Somewhere here, also somewhere, anything, anywhere inside this shaded area, but not outside here, not here, not here. So we are done with the first constraint. We do the second constraint. What's the second constraint? The finishing hours, finishing time. Okay, finishing time. So we do the same. This is the finishing time. Let's find the x, the same method, find the coordinate. We need 2 points to draw a straight line. If x1 is 0, if x1 is 0 somewhere here, 0, x2 is You calculate, assume given, or you want to calculate? Okay, let's try. If x1 is 0, 400, we get 300 something.
320.
320, yes. 320, we already marked here. Now, if x2 is 0, if x2,
480.
480.
480. So 480 somewhere here. So we plot the thing, and x1 is 0, x2 is 0. I think you can conclude this side or this side. The first one or second one, the feasible area.
Second one.
Second one. So this is the feasible area. Good. So far, so good. Let's have another one. We have 3 constraints to plot. The third constraint, just now the requirement, the 40% requirement, we have formulated something like this. Now I put the 4x1 on the right hand side. It's the same. The same thing. We want to find 2 points to draw a line. Now, if x1 is 0, okay, you can answer me already. What's x2?
0.
0. 0. We have put point here. So this is 0. Now, if x2 is 0,
Also 0.
also 0, then how are we going to draw a line?
We need another point.
We need another. I thought you were going to punch through your paper. So we need another line. So let's say put another line. Let's say I put x1 300. If x1 is 300, 300 times 4 is 1,200. Then put to the
X2
right.
is 100.
200, right?
Yes.
200. You have another 1 point, 200. So we have another point. Okay, now you can draw a line. Since it's linear, we can draw the line. Very good. Now, where is the feasible area? This side or this side?
Yes.
Upper side. Lower side or upper side?
Upper.
Upper.
Yeah.
Fatia say upper. How do you know? I do not know, sister. Let's find out how to do this. It could be lower, it could be upper, which we do not know. But maybe your sister's guess may be right. Or sisters already have intuition, already calculated. Let's test a point. S1 is S2. Let's test a particular point. If x1 is 400, x2 100, somewhere at this point. Somewhere at this point. x1 400, x2 100. Try substitute this number into these equations. What do you get? If x1 is 400, x2 is 100. Yeah, what do you get? What number do you get?
1,000.
1,000. Plus or negative 1,000 or positive 1,000?
Negative.
Negative. Negative. Sure? Negative 1,000. Is negative 1,000 greater than 0? No. So it failed the test. So you get negative number supposed to be greater, you violate the constraint. Okay, let's test another point. Let's say no, we test somewhere here. X1 100, X2 400. I think you can speculate the answer, but let's just verify this. If X1 is 100, X2 is 400, what do we get? Positive number, right?
Yes.
Positive?
Around 1,000.
2,000. 2,000. So it passed the test. So it satisfied the constraint. So which is the feasible area? Up. Yes, my sister say up. So the feasible area up until up to the sky. Okay, let's put all the constraints together, superimpose over each other. Is this the first constraint? We put it less or equal to. And then the second constraint, less or equal to. The third constraint, this one, and greater equal to up here. X1 greater than 0. X1 must be to the right. X2 upward. Okay, now, if I were to produce, what number here? Somewhere, if I were to put a coordinate somewhere here, 200, 200, do I comply with the constraint? All the three constraints? If I were to produce 200 X1 deluxe, 200 X2 special, do I comply with all the constraints?
No.
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 No. If I were to produce 200 and 100?
No.
No. Somewhere here?
Yes.
Here.
And
Yes or no?
No.
No. Erna say no.
No.
If I were to produce 100 and 200, 100 deluxe, 100 special, do I? Okay.
yes.
Yes. The same thing if 100, 100. That, do I comply with all the constraints?
Yes.
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 Yes. So we are actually having this area. Anywhere in this area, we comply with the constraints. So we refer this as feasible region. Feasible region. That means a bounded region. We call this bounded. It's bounded by the constraint. So we get the feasible region. Let's solve our problem. How many deluxe, how many special, using what we call it corner point method. What we are going to do, we are going to find the corner of this feasible region. We are going to find the corners of the feasible region. Let's say name O, A, B, C. Okay, see next slide. So we name it as O origin, A at this point, B at this point, C at this point. Can we find the point here? Here is 0, 0. At this point, I think you know the answer, 0. Here, can we find? We solve the equations, right?
Yes.
Okay, we don't go into detail. We solve these equations, then we can get this point and this point. Let's say these are the coordinates. These are the coordinates of O, C, B, A. Now, what do we do next? What does this left-hand side represent? Yeah, substitute. This left-hand side represent X1. The right-hand side represent right-hand side X2. That means the left-hand side is deluxe. The right-hand side is special. Let's substitute in our objective function. This is the objective function. I just rewrite it here. If you were to substitute all this, let's say consider done. These are the answer. If we produce nothing at this point, x1 is 0, x2 is 0. That means we produce 0 deluxe, 0 special. What's your profit?
0.
0. So the same thing, if we try to substitute this, we get this value of Z at the point here, point here, point here. What is our purpose just now? The objective, maximize or minimize?
Maximize profit.
Maximize. So which of this give you the maximum profit?
Point B.
Point B. So Z at B is the optimal solution. So how many units of deluxe should we produce?
120.
120. How many units of special should we produce?
240.
240. So that is the answer. 120 units of deluxe. That means X1 equals to 120. X2 equals 240 with Z equals 3840. Let's use another method. We call it, so at this point, we refer this as extreme points. And then you use eyeball, using the eye only. You can have some estimate. Here 133, here is about 240. But when you solve this equation, you get more detail, 133.333, here 240, and so on. Another way of finding this one is using isoprofit line. How to do isoprofit line? What we do is we make some assumptions first. This is the objective functions. Now we are going to put a hypothetical profit first. This assumption is just guessing, or you can use this way: 12 times 10, you get 120, but the number becomes too small. So let's put some number. If Z equals to 2,200, we try to plot the line using X1 is equal to 0, like the way we plot the constraint. You get this line. Then if we increase to 3,000 profit, the thing goes away from the origin. Away from the origin. If you put another assumption, say less, it will go towards the origin, getting less and less. Now it's going away. So now instead of try to put number, maybe we have to put a ruler. Try to have a ruler with a wheel, we have ruler and roller on the left hand side, and then another roller on the right side, and then so that it moves parallel to this one in that directions. Let's say we have something like that. Move, move, move. Then if I were to move again, what happened? It would go out of the feasible region.
Yes, the
Yes,
area,
it
feasible
will go.
region.
It will go out. So here it just touch at this what we call extreme points, somewhere at this point. So this is at this point just touch. So we move it. So from there we can solve these two equations, this two constraint, or looking at the graph. If we are using graph, try to, if your graph is very precise, get this one. So this is using isoprofit line, and this line it refer, get this one. So we refer this as isoprofit line, and the solution is 120, 240. Okay. What if this time we change the objective functions. Now the coefficients we change from 12 to 20, and here 10 to 15. Let's say we do this one. If we were to plot the, say, also profit line, it may coincide somewhere here. So this is the same set of constraint. Now we get somewhere here the optimal point, the extreme point is at A and at B. Then the coordinate at A is 200 and 1333. If you are going to calculate, you are going to substitute 200 here in x1, 133.33 in x2. What do you get? Try. Anybody calculating?
So what is it?
Try to substitute 120 in this new objective question, function. One, say the first one, 200, say x 200, x1 200, x2 133, x2 1333.
6,000.
6,000. Now you try to put 120 to 40, 120 to 40.
6,000 is
6,000.
6,000 also.
6,000 for B.
6,000 for B, 6,000 for A. So both 6,000. Okay, let's have another point. So you get 6,000. Let's try somewhere here. Say x1 150. Somewhere here. x2 200. What do you get?
6,000 also.
6,000 also. So what does it say here? The solution will be anywhere along this line will give you the same solutions. That means if you are the manager, if this is the objective functions, you look at these objective functions, it almost coincides with this constraint, or it coincides exactly 6,000. So if you are a manager, you have choices. You can decide to produce 150, 200, or any point here at point A, at point B, or anything you select. So you have more flexibility when you encounter situation like this. Okay. Okay, let's look what we call it, binding and non-binding constraint. What's binding? Let's look into the first constraint. Let's go back to the original again. The objective function. The original was 12, is 10. With the optimal point, 120 and 240. If I were to substitute this value in the first constraint, this is the profit. You have the first constraint was 20x1 and 15x2. x1, x2. If I were to substitute 120 here, 240 here, you will get 6,000. Okay, are you following? You want to try? So I refer this left-hand side value. This one, I call it right-hand side value. This one, because we compute. This one is, so this means the carpentry hours, sorry, the construction minutes all the construction minutes is fully used. Because you are given 6,000 minutes. So when you really produce 120 units of deluxe, 240 units of special, you fully use your construction minutes. Anybody substitute this one? This one? No. Okay, never mind. Let's put another. So this is for this constraint. Okay, try this one. Now the second constraint is the finishing hours. Let's substitute this 120, this 140 inside here, x1, x2.
4,800.
Also,
You get 4,800, 4,000. That means your what is this finishing, is it finishing hours or minutes, you make full use of it, none left. That means none is not utilized, so fully used. Let's look into the third one. So this for this constraint, that's the third constraint for this one. You substitute this one, you substitute this one inside these equations. What do you get? Let's say you get 960. You can test. 960 is greater than 0. Okay, you comply with the thing. But this number, that means represent, that means we produce 960 units more by using this constraint. What happened is these two constraints, the first and second, intersect at the optimal solution, at the extreme points. And intersect, we refer this as binding constraint. Second one also binding. And this one doesn't intersect here, is non-binding. Okay. The difference between, look into this one, left-hand side and right-hand side, what is the difference? 0, right? You subtract this one minus this one. What is the difference in
0.
0? Here, 0. Here is non-zero. Because I have not teach you about slack or surplus yet. Here, 0 slack also. That means all resources used. There's no idle resources. Idle resources here we call it, when we have greater, we call it surplus resources. That means, so if this is not 0, we call it non-binding. Okay. So constraint that intersect at the extreme point are referred as binding. If it doesn't, non-binding. Even if you have more than one, anything that intersect at the optimal point is binding. Okay, I think I want to finish off this one. Can we rest 5 minutes, 5 minutes, or 3 minutes? Or you do not need rest?
Yes.
Okay, okay. We rest a little while you are resting. You want to take a sip of your coffee or what? I want to ask me anything, by all means. I'm not sure what do you write in chats. There's nothing. Okay.
Sir, why mute?
Unmute. You want to ask something?
No, sir. I'm good. I'm good.
Because I don't want you to see me drinking water.
Oh, it's okay, doctor. You can eat or drink nasi if you want.
You bring me nasi lah. You want 5 minutes or 3 minutes? I think enough already. Can we
I think
resume?
it's enough, sir.
Enough. Okay, let's resume. Just now we did maximizations. Now let's look into cost. When it comes to cost, what do you want to do? Maximize your cost or minimize your costs?
Minimize.
Minimize cost. Okay, let's look into minimizations. So let's say cost. So the method is exactly the same. Except now when we look at the value of Z, we look into the minimum. Very simple. Let's say we have this statements. As part of quality improvement program, Thomson Electronics Sdn Bhd offers its employees a 3-day training program on teamwork and 2 days training program on problem solving. So we have 2 different training, teamwork and problem solving. The first one take 3 days, the second one take 2 days. And then the director of the quality control units has requested that at least 10 training sessions on teamwork and at least 12 training sessions on problem solving to be offered during the next 6 months. And the office also said, in addition, he has specified that altogether, at least 30 training sessions should be conducted. That means total 30 training. And then Thomson Electronic has appointed a trainer to teach the training program. And in the next 6 months, the trainer has 90 days available. Each training sessions on teamwork costs 8,000. And then on problem solving costs 6,000. The question is, how many training program on teamwork and how many on problem solving should be conducted in the next 6 months so that the total cost is minimum? Okay, solve this graphically. Formulate the problem and solve this one. Okay, let's do quicker. I think we are not going into detail anymore. We just try to figure out. Let's X1 number of training, teamwork training, and then X2 problem solving training. Then the objective is minimize Z, minimize cost, 8,000, 6,000. Okay, let's look back. Minimize 8,000, 6,000. Okay. And then subject to the first one, teamwork. Okay, how does it say? At least 10 training on teamwork, at least 12 training on problem solving. That means not less, right? Not less, not less. So not less, let me see. Put greater or equal, greater or equal. And then we have, and then we have the trainer The trainer say they had 90 days available.
Saya
90
kalau
days.
tiba makan benda yang
Nan-
susu lebih pening.
90 days available, and then each teamwork 3 days, and then the problem solving 2 days. Okay, back to, so we have 3 to 90 days. Okay, any more? Do we miss any points? All together, does it say somewhere? All together, at least 30 training sessions. At least 30 training sessions. So we have 30 training sessions. X1 and X2 non-negative. So we have this formulation. So we have these formulations. Let's solve it graphically. So let's these are the formulation, and then we plot the line. X1 10 greater or equal on the right hand side. X2 is 12 somewhere here. X2 12 greater or equal to 3x1 3x2. If you do the step by step, this is the line. Less or equal to, and then the total training here, the last one, greater or equal to. Where is the feasible region? Here, somewhere here. Let's say this is the feasible region, somewhere here. This is the feasible region. So the same thing, we find the coordinates, the corner points using corner point method. After finding the corner point method, we substitute in this one, we get the value of cos, ZA, ZB, ZC, ZD. Now it is minimizations. So what is the optimal point here?
Point D.
Point D. So how many units of teamwork and problem solving? 10 and 20. 10 and 20. So that is the solutions. Even if we use the ISO cost line, just not ISO profit. Now we are looking at cost. We look into the lowest extreme point. This is the ISO cost line or Z line. Good. So let's look into another special cases. We have situation where we cannot find feasible solution, or we cannot find bounded solution. That means we cannot find a solution, or we have more than one solution. I think we discussed this just now. Okay, let's look into these scenarios. Let's say we have this formulations. We are given this model, linear programming model, and we try to plot graphically. We get this is the feasible area for, this is the feasible area for the first constraint, and this is the feasible area for the second constraint. And we cannot get any bounded area, no feasible region. So situation like this is not feasible. Why does it happen? Maybe the problem is not clearly understood or not really well formulated. That means there are some items which is missing. So the problem statement have to be clearly said so that we can avoid situation like this. Another one is unbounded solution. Let's look into maximization case. If you were to look into this one, X is the second constraint, X2 is less than 5, less than 5. The first one, x1 minus x2 greater than 8, somewhere to the right here. So when we do the feasible region, we go and go on endless. So you cannot find any solution. But if it is minimization, because you are going to this direction, we can find a solution. If it is minimization, the solution could be at this extreme point or at this extreme point. In this case, I don't show you the solution, but I just want to highlight unbounded solutions. For scenario like this, for maximization, we cannot find a solution. For minimization, we can find a solution. Another one, we have more than one solution. Situation like this. Let's say we draw the ISO, this is a maximization, let's say profit. When we draw the ISO profit line, it coincides in one of the constraints. Okay, let's say this one. This is the constraint line. When we draw the ISO profit line, coincide. That means and then we have this less than 15, less than 72, less than 15. And these are the constraints we have already plotted. And this is the feasible area, sorry, feasible region. And anywhere along this line are optimal. Then we have more than one solution. More than one solution. Over here, over here, over here, over here. Give you the same solution. So we have it. Or we call it alternate optimal solution. How to detect? You can see this one. You see the objective function maximize z x1 equal to 3x3. You look at the one of the constraint, we have x1 plus 3x3. So from here, I think you can guess the profit is 15. Somewhere here, 15. Because here is 15. Okay. Another scenario is if we have this linear programming model, we try to plot. We already plotted. And we have the feasible region here. We found the feasible region. This is the bounded region, bounded by two of the constraints. And then we have one constraint here. If it is not there, can we find a solution? If this constraint is not there, can we find a solution? Anybody there?
Yes.
Yes. That means this green constraint, that means
Not
this
needed.
equation, whether it's there or not there, it is, you can still find the feasible region. So we refer this as redundant constraint. Not that the constraint had to be thrown away. This constraint may be necessary as one of the resources. Maybe this value make it redundant. If the value here a little bit lower, maybe the line is somewhere here. Somewhere here. Somewhere here it become bounded. So a situation like this, we refer this as redundant constraint. Okay, no need to go to this. Yeah, done. Okay, I'm done. I think we cover in one class this particular graphical method. Any questions? I think those who have done operations management, I think you don't have problem on this one. But I think some of you are from doing BBA, I think it's new to you. Any questions? No question. Okay, I
So
stop
far, so
sharing.
good.
So far, so good. To display this. 1 minute. I still have to learn something. Let me share again. Okay, now stop share. All right. No questions? If no question, can we do Suratul As?
No.
Sure. Then.
Okay, let's end our day with the recitation of Suratul As. Bismillahirrahmanirrahim. Wal asr innal insana lafi khusr illa allazina amanu wa amilus solihati watawassaw bil haqq. Thank you very much, brothers, sisters. See you next class.
Thank you,
Thank
Doctor.
you, sir.
Thank you,
Thank
Doctor.
Waalaikumsalam.
Thank you, Doctor.
Waalaikumsalam. Okay, bye-bye. Waalaikumsalam.
Thank you, Doctor.
Waalaikumsalam. Okay, I
Thank you,
end the
Doctor.
Thank you, Doctor.
Waalaikumsalam. Welcome. So I end the class now. Assalamualaikum warahmatullahi wabarakatuh.